Hi, my name is Sean Johnson. I am the Technical Community Manager for the Vesuvius Challenge, and this is an introduction to nnUNetv2 on Vesuvius Challenge data. This is also operating as a office hours session within our Discord, and so there might be some times when I'm helping other people out or answering questions if anyone's asking them, but you can also use it as a guide or a starting tutorial to processing scroll data and doing semantic segmentation on Vesuvius Challenge scroll data. Just to start, we'll go over what nnUNet is. nnUNet is a framework for conducting semantic segmentation. It's not so much an architecture as it is, it's just a methodology for performing semantic segmentation. The primary thing it does is self-configure. This is kind of what it's known for. It has a list of rule-based parameters that it goes through to configure the architecture of the network and the normalization schemes and spacing for your data. You can see some of the rule-based parameters here. But what it does is during the pre-processing stage, it just goes through all your data and tries to identify what you could consider to be like best practices for handling the data that you're in. And this is a thoroughly tested methodology, and nnUNet is very performant in medical imaging, which has a lot of similarities to what we're doing in that it usually uses CT scan data or MRI data, and it's volumetric data. What this process does to determine that is it goes through your stuff and it extracts what they call a data set fingerprint, which you can see here. And then there's some stuff that isn't configured by the parameter, the auto configuration, and that's still relatively configurable within the nnUNet scripts. Why to use it? It's good. It's very good at what it does. nnUNet is very commonly used as the starting point for many medical imaging competitions, of which there are many. It's well tested. It's been around for a long time. The people who created it have won a number of these medical imaging competitions, and it has a ton of support and use in the community. Also, it's pretty easy. It does a lot of the stuff that you have to do when you want to test out different things, different architectures or networks. It does a lot of the stuff that you would otherwise have to write up on your own. That takes a long time. All of the data loading, normalization schemes, all of that stuff, nnUNet handles for you, and so you can focus on trying out different things with your data, different normalization schemes, different loss functions, things like that, without having to go through and rewrite all of that stuff. What does it configure? So it automatically handles the intensity normalization. It has a few intensity normalization schemes, which I'll go into later. It handles the resampling of your data if your data has different image sizing or spacing. Handles your patch size automatically. It tries to determine based on a set amount of VRAM and the median size of your data what a reasonable patch size would be. Does the batch size as well. By default, it's 2. Typically, you're going to end up with 2 with volumetric data unless you have a giant graphics card. So for me, I have a 24 gigabyte, or I have a RTX 3090 with 24 gigabytes of VRAM. So typically, my patch size ends up being 2 for 3D data. For 2D data, it's a little different. And then it configures your network topology automatically. This is done by taking your patch size, which is like kind of your starting point for all of your topology, and then figures out how many times that data can be downsampled and then later upsampled within a reasonable size. So you don't want your downsampling stage to end up with your data being so small that the network can't learn anything from it. And then based on the amount of stages or downsampling stages you can do, that sets the feature map size. So by default, let's say you start with a 128 cubed volume. If you downsample it once by 2, you go to 64. So by default, your starting feature map size is 32. Your first downsampling size will take your 128 cube and make that 64. Your feature map size is now also 64. Down one more to 32. Now your feature map size is 128. So it doubles the feature map size for every time you go down. And the number of blocks per stage is defaulted at, it does 1 to start with, and then it goes to 3 and then 6, and it maxes out at 6. And your feature map size maxes out at 320. So it'll downsample and double your feature map size until it reaches 320, and then if it can continue downsampling, if your volume is large enough, it will just repeat 320 every time. And the reason it does that is just to prevent your feature map and learnable parameters from exploding. And it works pretty good. I've practiced with doubling or increasing that significantly up to like 512 or even 768, and it increases your VRAM cost substantially, but it doesn't increase your performance that much. You might have to practice with that if you've got more complicated data. All of your kernel sizes are set automatically. These start at 1 and end up at 3, and they're just 3 all the way through. Your gradient normalization is handled for you as well, and then your stride and dilation. Stride is the same. It starts at 1 and it goes to 3 as quick as it can, and then it just sticks with 3 for the rest. And then it handles dropout, which by default is off. The things that aren't configured by the auto configuration steps, and these are just fixed because they're empirically good, so they don't really have to change it very much. Your optimizer, which is just standard SGD, using momentum. You can modify this by using an alternate trainer. They have a few of those. They have Atom as well. Your learning rate is fixed at 1E2. The scheduler is fixed using a polynomial learning rate scheduler, which means it just steps down by a fixed amount every time with the goal of reaching 0 by the end of the training. You can modify this to use cosine annealing by just using a different trainer as well. I don't think there's any other ones. I think it's just polynomial and cosine that are implemented, but you can choose a different one by just importing the torch module. It's very easy, and I'll show how to do that in a little bit. Weight decay is hard set. You can modify that if you want. Also pretty easy. You just modify it in the trainer. And then your loss functions by default are just a compounded loss of dice and cross entropy. There's a very tiny degree of label smoothing there, not a ton, and that also is configurable. And then the augmentation. Augmentations are very easy to implement, and nnUNet by default uses a library also created by DKFZ called batch generators. There's 2 versions, and it uses a little bit of both of them. You can change this though too. It's very easy to add augmentations, and I'll show how to do that as well. The biggest thing with nnUNet is you have to tell it, because it has a number of scripts included within it, and a lot of different parts of nnUNet handle different parts of the training and pre-processing. You have to tell nnUNet where your data is, and the way you do this is just by setting environment variables. In Linux, this is done by just exporting it. You can do that right in the terminal window you're in, and it'll set it for that terminal session. Or you can do it, you can set it in your, to load up every time by just changing your bash RC. I think that's what it's called. I always forget what that's called. I just do this every time. And I'll put all these commands in the chat as well. One second, let me copy these. I'm just gonna copy all of them at once, and then if you need any, you can grab them. The dataset format for nnUNet is kind of fixed. So you've got to have your dataset in a format so nnUNet knows where everything is. You can either have it in need.gz or nifty or 3D TIFF format. You can have other ones, but this is the primary way for volumetric data. It can also read PNGs, but for the purposes of us, it's typically either going to be in .need.gz or .tiff format. And within each one, you need a dataset.json, which tells nnUNet how many training samples to expect. These are placed, and then you need an images train folder and a labels train folder. You can also put whatever you want in there. You can put other things in this folder, and nnUNet won't like throw errors or anything. So I tend to store actually a fair bit of stuff in there. I'll store different types of that data. If I've got, say, labels that are some are thicker, some are smaller, I'll store different samples so I can just quickly swap those out and not have to like go digging for the data. Each file, you'll see each image, you can see here, has a suffix, and this suffix is indicating the modality of the data, which maps it to a normalization scheme. You can pick a bunch of different normalization schemes, but you'll set that mapping in your dataset.json, which I'll show in a little bit. Each image needs a suffix, and each label should not have the suffix, so they should have the same name, but not the same suffix. Your dataset.json looks like this. It has a few things in it. Channel names, this is the mapping I was talking about. So you've got the 0 and then CT, so that's the mapping for normalization. So it's just a key value pair for suffix normalization scheme. You can add your own in here, and I'll show you how to append that later. Your labels, these have to start from 0 and increase sequentially. They can't have any gaps. You can have as many labels as you want in here, and you have to have the background class of 0. Then you have your number of training. That's just the number of image label pairs. The file ending, that's obviously the file ending of your images and labels. And then you don't actually need this. I have this in here right now because you used to need it, but this is just the image label writer. For TIFFs, it's just TIFF 3D.io. And then for 2D images, you use the natural image writer, but you don't actually have to include any of that. Once you're ready to start training and you've got your data set all in the right format and the right place, you can run the pre-processing step. So nnUNet runs through a pre-processing step for all the data. What it does during this step is it extracts all your image and label data and it stores it as on-disk uncompressed NUMPY arrays, and this is just to speed up training and then to ensure that all your data is in the proper format to be loaded into the data loader. It finds the global min and max and the standard deviation of your intensities, and it stores these values in your plans.json, which we'll show in just a little bit. It also determines your median image sizing and your spacing and uses these to configure your stages and your feature map sizes. And then finally, at the end of it, it writes out a plans.json file, which contains all your network parameters. And this is needed because if you go to do inference with your model, it needs to know how to build it, and all that's stored in there. It's also nice just for debugging, or if you're going to check what parameters you used when you ran it. Maybe you have a model that ran really well and you want to find out what caused it to run well. You can just check your plans.json file. You can also change it. There's a ton of stuff you can do with that. I'll go into there. There's a link I have in this slide, and I'll actually send the slide here in just a second to the chat so you can go through them. But this is a huge benefit to using nnUNet. You don't have to change anything but the plans.json file, and you can change the number of stages, you can change your patch size, your batch size, you can change your feature map size, you can change everything more or less through the plans modification without writing a single line of code. To run the plan and preprocess stage, you just type this command once you've got all your stuff set, and this D is your data set number, which is, if we go back to the example here, it's 01, and then so you would type 001 here, and then the plans is the plans you use to build it. I have the nnUNet ResInc plans here, and the reason for that is because right now nnUNet is going through a bit of a transition from using just standard convolutions or standard convolutional blocks during the as their network architecture to using residual blocks, and right now they have those split. This is the recommended default is the nnUNet. But you have to still put that here. If you don't want to use residual blocks, and in some cases that's not a bad idea. In some cases they're just more than you really need, and also they increase training time and VRAM cost. You can just omit this and run it without the nnUNet plans. The normalization, I just want to go into this quick because it does matter for some of the data. So for CT normalization, it takes all those intensity values that it gathered and all that information that it gathered in the pre-processing stage, and then it subtracts the mean and then divides it by the standard deviation. And it does this along only the foreground parts of your data, and it does that by using the label that you've provided it as a mask. And the benefit to that is it tries to enhance the contrast of but primarily what we're looking for. Especially in our data, if you do a mean and standard, or if you do like a standard deviation normalization like this on our data, especially like in scroll 5, it doesn't have a lot of intensity by default, and it can, if you're not careful with what you do in your normalization stage, you can wash out your data, or you can end up with very dark data. This CT mapping is what we saw in the dataset.json earlier. You can change this to whatever you want. If you don't want to use CT normalization, you could do no norm. Maybe you want to handle it on your own. You would just set that in the dataset.json after your 0. Same thing with this rescaling or RGB or Z-score. You can do all kinds of stuff there, and you can also define your own normalization scheme. Z-score is the default. If you don't specify CT or you don't specify anything in there, Z-score will be the default. So we ran pre-processing. Let's say we ran pre-processing, and we can walk through this, and I can help anyone through it after we go through just kind of a walkthrough of the whole process. Let's say we've got that done. We want to start training. When we are training, there's a ton of stuff that gets printed out in the terminal. First, it's gonna display your entire network configuration, and then as it trains, it'll show a EMA moving dice score, which is just computed on a random validation patch. So you shouldn't really take this as gospel, but when you do a lot of training runs, you kind of start to get a feel for like what is a good one, even on your data. For me, typically, like if I get to like 60% on surface models, I know I'm training a pretty decent model. So you've got to train a couple models just to get an idea of like what's good. And this is kind of, if you look at like average dice scores or IOU scores for like a lot of other medical data, you'll see it like crazy high, like 98, 99%. For our data, we can't get there quite yet. We just don't have the labels for it. So don't get discouraged if you don't see this super high. It doesn't really matter what the absolute value is. It just matters if relative to your other models or relative to our other data, if this is a good score. Also just prints out your epoch time, which is nice to see if it goes up really high or down really low, just to kind of watch how your computer is handling it. And here you just specify the plans file that you used earlier. If you did not use the nnU-Net plans, then you wouldn't need that either. By default, nnU-Net has it breaks your data up into different folds, 5 of them, so it finds a way it can split your data 5 times, where 30% of each fold will have a different set of validation data. If you want to just train a single fold, you just specify the fold number here. If you don't want to do any validation at all, you could just put all here, and it'll just use all of your data for training and not do any validation. But keep in mind that this number then, your EMA best pseudo dice, is not exactly accurate because it's computed on data that you're training on. If you want to modify them, you can go into your splits final.json file, which is created when you first run training. I'll show what that looks like in a second here. And you can just move those around. I do this usually because it's really hard to gather data for the scrolls, and so I don't want to waste all of it on validation. And it's not really a waste, I guess, but like it takes so long to get it that I want to use everything we have. So I don't run all because I do want some validation, but I do modify by default. I don't use 20% of it. I use like maybe, I don't know, 5 or 10%. And then inference is just another simple command. And we'll go through this in a little bit. But the main thing to know here is that, well, there are 2 things. Number one, your images have to be able to fit entirely in memory. And this is one somewhat difficult thing about nnU-Net, especially with our data, is you'll have to probably break it into blocks because there's no way you're going to fit an entire scroll volume in memory unless you're renting a server with an ungodly amount of memory. You'll almost certainly have to break it up. And it merges these so you can feed it. It doesn't have to be a patch size, but it has to fit in memory. So what I typically do is I feed it 600 by 600 by 600 blocks, and it'll iterate over that block with an overlap of 50% and merge those windows with a Gaussian importance map. It does a really good job. nnU-Net's fantastic at this spot specifically, more than like anything else I've ever seen. It doesn't really have any patch edge artifacts, does a very good job of that, and it uses test time augmentation, so rotations and flips. Actually just does mirroring. It mirrors your axes to kind of emulate a rotation or flip, and then averages those together. The inference time on nnU-Net's not the best, but it does a good job, so I use it. You could modify it and use a different inference loader or a different prediction thing. You just have to know how to load the model. Extending nnU-Net is, again, one of the best parts about it. This is an example of the plans.json. So say you wanted to add another level, you wanted to add another downsampling stage. You just change this to 7, add another feature map size, add another set of kernel sizes, and you're done. You can change just about anything in it. You could change these. You could change your network architecture class name. As long as it's from dynamic network architectures, you could import. They have a full ResNet. They have a graph neural network in there. They have plain convolutional networks. They got a lot of stuff. But you could change this. I mean, this all this does is it maps this string to an import. So you could really import whatever you wanted. You can also change the trainers. What's really nice about this is nnUnet's base trainer. Everything about it is a method of that class. And so if you want to change anything, it's as easy as just subclassing the nnUnet base trainer and then overriding whatever method you want to change. So if you want to change your loss, you just subclass the trainer and then override build loss. And that's it. Everything else is still handled. You don't have to write a whole new trainer. This could be even shorter. Say you subclass, you didn't want deep supervision, and you do need to specify this. If you do change something, you'll have to handle the deep supervision part, unless you subclass the no deep supervision trainer, which is you just change this up here. But if you subclass to the no deep supervision trainer, this is the only part you'd have to change. It's just loss equals whatever you want, return loss. And you have your whole training thing done. And then when you call training, you would just do dash trainer, whatever you called yours. You can also do a lot more. Loss is an obvious one, but you could do anything you want. If you wanted to do seg-resnet like with Monai or some other architecture, maybe some kind of other transformer architecture, something like that, all you've got to do is you can literally import seg-resnet from Monai and then just say model equals seg-resnet and return the model. And you're using a different model. The only thing you have to keep in mind is that it has to be able to handle the patch sizes and the batch sizes you throw at it. Say you use like nnUnet, that uses a much higher VRAM for a given patch size, and so you'll want to keep that in mind if you do this. But it's pretty easy, and I'll also link a trainer that has a lot of these as well when I post this. So that's it for the slides, really. I'll go through then a training thing. Do any of you guys have any questions at all so far? It is recorded too, by the way, if you missed anything in the beginning. I'll post the recording as soon as we're done. Okay. So I have this data pre-processed, but I'm going to run it anyways. I have a small test set that I put here. In community uploads, I'll copy the link to that right now. If you want to follow along, let me know. I'm gonna wait about a minute to see if anybody is following along, because if you are, I'm gonna give you a little bit of time to download it quick. Otherwise, I can start. Okay. Doesn't look like anyone for now, so I'll just go ahead and start. So first thing, I just got to set my environment variables. I think I already got these set, but I'll do it again. Again, this is just specifying where my nnUnet raw is. All of my dataset folders, basically. I have these stored in a datasets folder, and then they're just these three folders: nnUnet raw, nnUnet preprocess, and nnUnet results. You don't have to call them that. You can call them whatever you want. I just stick with that because that's the default, and it's easier for me that way. We're targeting here when we run our nnUnet preprocessing stage is it'll target the data in nnUnet raw. My test one that I just copied here is right here. I just have it called Frangi EDT test. Yeah, I know they do. It's kind of strange. I don't know. So this is my dataset.json here, which I think is the same one I posted, but oh, dragging the wrong thing over. 1 second. There we go. So that's the one for this one. And actually, this is a, a good chance. So my num training is wrong. And if I ran this right now, let's see if we can get it to throw an error. This is a common error that you will encounter when you're doing this, is that you've got your train size wrong. So I've got a little bit, let's see, 34 res. Let me just put some spacing between these so I get the right ones. So I'm going to run this command, which I'll just throw in the chat in case anyone wants to do it. And it should throw an error. Oh yeah, plans. Fun. Okay, so let's do this then quick. It can't find the pre-processing class because I probably got the wrong one. So first I got to fix this to 89, which I think is the number. Yeah, 89. And then I got to re-grab my pre-process. I copied a couple over and made some changes to them, but I apparently copied them incorrectly. Let's see if we can find it here. I have a large file where I like just kind of copy these commands one at a time, because if you're running a lot of different trainings, you'll end up where, like, say you're running 5 trainings, like this is an example of running four different ones or 4 different predictions. You're making just very slight modifications at a time, so I just kind of keep some of those commands around. So here it's first going to just run through every single image I have and just compute those statistics we were talking about. You get these extra things printed out if you run with TIFFs. Because TIFFs, unlike Nifty files, don't include spacing metadata, you would have to specify your spacing if it were not isotropic, which our data is, which means it's the same voxels in every direction the spacing is. It's not always the case with CT data. Sometimes one voxel means more than one in one dimension, or less than one in one dimension. For us, it's isotropic, so it's all the same. So I just let it create a spacing file for each one, which stores itself as a spacing.json file, which you see in, you won't probably see here, but you'll see it when you run inference. Let me just check. This one was 060. So here's the raw NumPy ones, and then a pickle file, which defines a few things. Okay, so yeah, you don't see them in here yet, but when you run inference, it'll produce a .json file for every single one of those, which just defines the spacing. But we've got that pre-processing step done. It's pretty quick with a small amount. When you have a large amount of data, it can take a long time. I also added this -C 3D full res because I don't care about, if you don't put this in here, it's going to generate information, or it'll run this step on each possible configuration, which would be 2D, 3D low res, and then 3D full res. I don't plan on using those, so I always just put -C 3D full res. You could play with that if you wanted to. On our data, typically, it seems that 3D full res is the best option. So now, if I want to train, all I have to do is run the training command. The parameters here are just the dataset name, so 060 for me, which you can find if you go into here, 060. It's just this little string of numbers right here. And then the configuration, which is 3D full res, which it pulls from the JSON, and then the fold, which is 0. The fold is determined in your splits final, which I don't have yet. It generates it on your first training run. I have an old one here, but I'm going to run it again. We can just pretend it's not. I'll just delete it. And then we'll just run our first training. And what I do, if I want to change the splits, I just cancel it right away. And you'll have your splits final folder or file here, and then you can just change whatever you want. Let me open this in VS Code so it's easier to see. If you were looking at this and you decided, hey, I don't want all these invalidation, you literally just cut them out and then paste them up here. So let's just do that. This is an older one I had open, but it should still work. You just got to make sure you put the commas here, and then there isn't a comma at the end of it. But that's it. So now I've changed my initial one said that we had 18 validation cases. I wonder if this is the right one. Pre-process test. Yeah, it should be. And now we've got 7. So it compiles it, and then it's got to unpack the data set first. This takes a little while. If you have got a very large data set, it can take quite a while. This one should go pretty quick. Yeah, it's already training. So we can check our usage. Yeah, I just saw that for us. Yeah, so he said it might be interesting to change the spacing, and I agree. There's actually, strangely, it has a bigger effect than you think on the data. So like when nnUNet wrote a paper called, when they first released these, let me see, it's under their repository, under documentation, oh, it's right here. And I'll paste this here quick. And in here, they found that like there was one of their tests, and I think it was during when they were testing MedNext. They went through and they tested nnUNet against all of these different architectures that have come out recently. Pretty much all of them, which have claimed that they destroy everyone else on benchmarks in standard paper format. And they tested nnUNet against all of them, and they tried to implement them using nnUNet's preprocessing, and then they reached out even to authors of some of these to help them get the best configuration possible that they could. And one of them, I think it was MedNext, strangely performed better using a specific spacing, and they found that when they changed nnUNets that it also performed better using that spacing on that specific data. So there is an effect on it. I just haven't gotten to doing a huge amount of testing here. But if you're ever curious about training times or VRAM requirements or anything, or you just want to see any information on other networks versus nnUNet, this is a good page to go to. It's just the Resync Prenets page, but you could also go to the actual paper. It's a good paper. Yeah, it has an effect. If you want to see then too, so I like to just verify when I'm going through here that I'm not destroying my VRAM and that it's actually running, that the data is actually loaded up into my graphics card, which it clearly is because we're training. But my NVIDIA SMI is so slow for some reason. But this one uses 9 gigs, so there's 89 volumes total. Doesn't keep each one in memory at a time, but 9 gigs of RAM for this, or VRAM for this. So you could use, if you use less images, it's smaller, or smaller images. And it doesn't use too much, 25 gigs of RAM. So you could run this on a pretty small machine, and that's one of the huge parts of nnUNet that I do like too, is that its requirements are very low. The standard one, the non-residual encoder, you can run with a very, very small amount of VRAM. So we'll let this train for a little bit because we're only at like 60-second epoch times, but let me go into the plans in a little more detail here while that runs. If you go through the plans folder, it's oriented or set up in a way where it has each configuration that's possible, and then the keys for that. These are global ones right here. Just some information, basically. There's not a whole lot you do with these. I always just scroll down then to this spot here, 3D full res, and this is the configuration for what you're doing. You can see my batch size is 2, my patch size is 128. If I wanted to change my batch size or my patch size, I could just override this by changing it to some other random number, 120 or 190. Or you should make them multiples of 32, though. I believe 32. Yeah. That's really the only thing. And then you could change your features per stage. Like I said here, it doubles each stage, reach 320, and then it just repeats. But you could change whatever you wanted in here. You just have to make sure if you add a stage, say you like add a stage here, if I added a 320, which would just add another one. If I change that to 7, you've got to make sure that now I've got another stage, so I've got to add another configuration for kernel sizes, and I would just do that by putting a comma here, copying one. Same thing in strides. And then nconv per stage, which is just the number of convolutional blocks. Let's say 2 again. And then the decoder is the same size, but 1 less. That's it. Now I've added another stage. So if I reran this training, it would use this plans.json file, which is modified. and it would create another one. We can go through the trainer for a second here too. Yeah, the differences in normalization across scrolls is actually pretty dramatic in our current one. They're all varying degrees of brightness substantially. And that's why they created the standardized ones, which do a pretty good job of equalizing that. But yeah, it does have a pretty big effect. I haven't tested out I tested out z-score normalization and CT normalization, and I found that the CT normalization tends to function a little bit better. But I haven't tested it in a very long time, and that's something that I should probably try again. Yeah, no, it does have a big difference though, and it does even through looking. It makes it really hard to do like ink detection when you go from one scroll that has good contrast and you can tell textures and stuff apart very easily, to another one that is very washed out. You know, some of them are very bright, some of them are very dark, depending on the scan. And they try to normalize the scans globally by computing essentially the same statistics that an nnUNet does, and then applying them everywhere when they merge the like slabs of the scan. And it works pretty good. It's just scrolls have such a varying degree of size and density, and we have a very low sample size right now. So it's difficult to get some kind of like global ideal setting, really. And then you don't want to influence like the data too much, because we don't, especially on scrolls where we don't know what the ink looks like, if we go like changing too much, we might impact our ability to actually see it. I'm going to just open up a trainer here. This is how the nnUNet library is formatted, where it's kind of broken up into different steps here, but your trainers are, yeah, and that's kind of why it affecting training on different scrolls. It's kind of why, well, it's exactly why nnUNet picks a normalization scheme for everything. So it tries to get all of the information to look the same. And this is the same thing you would do in like a medical scan. You would want all your information to be of the same intensity range, because, well, the model learns the intensity range. It learns that, you know, this intensity next to this intensity could mean something, and it could mean something else in a different one or a different place. And so it tries to make all of the intensity ranges the same, which you can't really do though in the scroll data as easily, because all of the scroll data is so different. And so it does help to look at the outputs of the normalization scheme and see, is it actually doing what I expect it to do, or does the data look terrible now? It's a good idea to check out every step really of your training process, to just visualize the data throughout. Anytime you change augmentations or transformations, anything. I've done a ton of trainings where I've made changes that I thought were one thing, and kind of just trusted that I did it right, and then gone through later and realized that I was giving it terrible data. You want to visualize every part of your process as much as possible, just because you never really know, and you don't really want to waste a ton of time. And things have different effects than you would expect frequently. Let's go through the training script real quick. Most of this is irrelevant to things that you would change, but it does help to kind of see what it looks like. This is just the default trainer. It imports all of the transforms you'll use later within here. It does, you know, its initialization, grabs all the stuff from the config.json, and then all of that is stored within a couple managers called Configuration Manager and Label Manager, and all of these are available throughout your training session. So if you ever need to get any information from the configuration, you can do that by grabbing it from the Configuration Manager, or the Plans Manager is actually what it's called. And that's how nnUNet kind of keeps track of all of the different things that it's doing. If you wanted to change some of your stuff, you can change it right here. This is one thing about nnUNet that isn't apparent initially. nnUNet does not iterate over your entire data set every single epoch. It has a max number of them of 250. So if you've got, say, 500 images, it will take 2 epochs to see all of your data. And so if you've got a lot of images, you want to keep that in mind, in that the performance epoch to epoch doesn't translate if your data set size has changed. So you can't really make generalizations about how quick something's learning unless you also take that into account. You can modify your learning rate, your weight decay, all that stuff. Max sum epochs, nnUNet runs 1,000. That's all it runs total. You could modify this, or you could go into, nnUNet has trainers for this. So instead of running the nnUNet trainer, you could run one of these trainers, which would be, say you only wanted to run for 100 epochs, you could just run nnUNet trainer 100, and that'll just do 100. And this is how nnUNet does all of its modifications to the training. You want to try to leave the nnUNet trainer, unless you're making a global change, you want to try to leave this one unchanged. I do change some stuff in here typically, just because I make changes that I know I'll always want to use. So like if I add an augmentation and I'm like, this augmentation always performs well on scroll data, or I like this augmentation, or I like this transformation or some setting, you can make that in here and it'll affect all of your trainers. But ideally, you want to try to leave this one as clean as possible so that you always have a true baseline to run your changes against. Most of this you would never change. Here's build network architecture. This is what you would override if you wanted to change your network. I've never changed the batch size or oversample stuff. You don't really have to do that. Build loss is within here. Again, just another method of the trainer class. This stuff I leave. This just determines whether you can rotate your data or not, and it determines what axes you can rotate your data on. If your data set is not, if your patch size is not all the same size, you can't flip it, right? So it determines which axes work for that. Then it prints the plans. This is where you could override if you wanted a different optimizer. You could replace this with Atom if you wanted to, and all you'd have to do is override this line right here, just configure optimizers. It's very easy. If you wanted to change like some kind of logging or something like that, say you wanted to write a debug GIF or something along the line, you could modify on train end or on train start or on val start. There's a lot you can do there. The other thing that should be in here is transform. It does use amp, yep. And you could turn it off if you wanted to. This the file is huge, so it always takes me a little bit to find it, what I'm looking for, but thankfully you can search. Here's where you would add. I don't. Thankfully, I've never had any issues with AMP, at least as far as I'm aware. I've actually never turned it off in nnUNet, so maybe it is affecting it negatively, but I've never got like any errors or anything from it. This is where you would, if you wanted to add augmentations or remove augmentations, you would override this get training transforms here, and then you can put whatever you want in there. The default ones are a spatial transform, which handles a number of different things. It handles the rotation. If you wanted to do plastic deformation, you could change this. It handles the probability of the rotation, the probability of scaling. It's kind of an all-in-one spatial transform that it bakes into here. And then each transform after that one is wrapped into a compose thing similar to albumentations or volumentations, if you ever use that. And then the random transform class, which will choose one of these to apply them to. And these are independent too, so if you stack these, you have a chance of having like all of them at once, or none of them at once, or some mix of that. And the probability is just set here, but by default it uses a pretty robust set of augmentations that have been tested quite thoroughly. So it goes through a Gaussian noise, a blur, modifies the brightness a little bit, does a contrast transform, simulates low resolution, and then it's got 2 gamma transforms for some reason. This is one I added to here by default, which is a blank rectangle transform it's called, but essentially all it does is just add a gray, or well, it's whatever the mean value of the rectangle around it. It just replaces that part of the image data with a blank rectangle. And then this is another one I added, which is it tries to illuminate slices differently. So like slice 1 and slice 2 would have some kind of slightly different defect as far as illumination goes. And the reason I added this was because our slices do. These aren't by default, but you can add these as well. These are just in batch generators. So if you want to add one, all you've got to do is either add it manually, which you could literally write it here if you wanted to, or add it to batch generators. And there's a lot of different ones in batch generators that are not used by default. And so it's probably a good idea to just go through that quick. And if you want to add one, is just check if it's even in batch generators first. Batch generators is pretty fast. They do a good job of keeping, they do. The slices, they don't vary substantially, but in certain areas they do, yeah. It's not a huge amount, but there's all kinds of different illumination throughout the scrolls, different artifacts from the scanning process, or if there's like a super dense object that kind of diffracts the light a little bit, or absorbs a lot of light, and then behind it it's darker, you know? And so there's tons of varying lighting throughout the scan. It's not a uniform intensity. The goal is to get as uniform intensity as possible, but it's just not really possible, especially with the scrolls that have like just an insane number of things in them, rocks and dirt and all kinds of different things, plus just the scanning artifacts that show up. But that's where all of your transforms are. I would keep these. Some of these transforms here are used within nnUNet and shouldn't be changed. These ones mostly. I wouldn't modify any of these ones. They're handled by different steps throughout nnUNet. And you could add some to your validation transforms as well. By default, validation does not have any transforms applied to it. That's pretty much the entirety of the training file. If you want to see, like, again, before you change anything, it doesn't hurt to go check, like nnUNet trainer. nnUNet has one with Atom in it. So you could just run this if you wanted to use Atom instead of SGD. And they've got a couple different ones with different learning rates and such. Do I inference on all of them? I'm a little confused by the question, to be honest. Do I run inference on all of the, so I do a test set the way I guess I test. I'll wait for you to just word it, and then I can make sure I'm getting the right question, or the right answer. Here's one for cosine annealing as well. So there's a ton of stuff you can change. This is how you would do losses mostly. I like this folder's here by default, and it helps if you kind of stick to the way they're doing it, because the library is gigantic, and so the more you change, the harder it's going to be to find what you changed, and so it's good to just kind of stick with what they have. I have a lot of stuff in a custom one that I have on my computer, and occasionally it's a huge pain to find where you've defined things, especially when you like define a new loss and you put it in within a compound loss here or something like that. Trying to find it again can be a challenge. So just kind of stick with their folder format is my recommendation. Here's like a different loss that I pulled from a different DKFZ library, and it just implements a skeleton recall loss, which just computes loss against a skeletonization of the label. And the way they override that is they just override the get data loaders, override build loss, and then the training transforms. I've actually added this training transforms one, added to it. By default, the only change here technically is actually they changed the they have like a skeletonization transform in here, but typically when you make like a loss change, it can be very short. This, for example, is the change to focal loss. So if I want to use Dyson focal loss, all I've got to do is change that. Okay, let's see. So if I'm doing inference on the GPRI, I do inference over the whole scroll volume. Oh, yeah, I see. Honestly, most of the time, so the normalization scheme is applied, the same one that you use during training is applied on inference. And that's important, and you'll have errors if you don't set it. What happens is when you run your training or when you run your inference, you need to have the same modality specified at the end of your things you want to inference on, so that it applies the exact same normalizations that it did during training to the inference stuff, because your model is used to the data looking a certain way. So if you change this, well, first it's going to throw an error, but if you manage to get through that, which you could by modifying the plans.json file if you were keen on doing that, it would not be correct. So you just got to do that when you do inference. Let's see where we're at anyways. Let's let it go for a little bit longer. So yeah, like ensembling. Yeah, and so the test time augmentation that's applied by nnUNet by default does a pretty good job, but I've never tried doing different augmentations. It might work. There's all kinds of stuff that works with it. I mean, it's really kind of like just trial and error, and I've kind of stuck with a lot of the defaults, minus like I've tried a bunch of different losses, and I've tried a ton of different data and architecture sizes and stuff, but I haven't gone and changed too much as far as like doing different augmentations other than the mirroring that's applied by default. So that's something that would be good to try. Absolutely. I would set, if a person was so inclined, that would be a good idea. You could set like a 100 epoch trainer and apply those different things to it, and then kind of summarize what that looks like. The hardest part of doing that right now is that our metrics are a little bit tough to come up with. Like, how do you know for certain if a segmentation is good globally? Because some models are better than other ones in small parts, and some models are better than other ones in different parts. And determining which one is the best overall is very, very, very difficult. And I haven't found a good way to do that. I'm working on a couple different ways to evaluate models. And it's something that we need desperately. One of them, so what I've done here is like I ran inference over a cube that was labeled with fibers and counted the number of ground truth or labeled intersections of the fibers, how many of them were intersected by the surface labels. And that seemed to be a relatively decent metric for like, has it performed it well? Has it performed the segmentation well? Because theoretically, the horizontal fibers should more or less always intersect the surface if we're predicting the recto surface. The issue with that, though, is like a model that just draws a blue square here will have 100% of the ground truth components intersected. And so by that metric alone, it would be a great model, but obviously that isn't a good model. So I'm trying to find what like a ratio of like, what is, for example, there should be a ratio of fibers to surface area. Theoretically, I mean, the fibers are consistent, they are regular, and so there should be, say it's like 15 or 20% for, say if you got 20 fibers, you should have 100 voxels of surface area or something. These are just random numbers, but there should be some ratio there that is accurate. And so I'm trying to figure out what that is, and then there should be some level of total surface area that we want our mesh to have, and we can kind of use that to determine how thick is the label. We don't want labels that are too thick either, because then you get merges like you see here. So I'm trying to find out like what metrics correlate with good performance, and that's very, very, very difficult to do. I haven't found a good one for that, and that's something we still need very badly. Yeah, no, if we have scans, I believe all the scans are out right now. Scroll 3 has 4 different energies, I think. Let's find out. I think scroll 3 has 4 different energies. 3 or 4. Let's find out. I haven't, that's a huge spot that's kind of untouched though, by the way. And what he's asking is, just so when this is recorded for later, is different energies of scans, and then doing some kind of like similar to like a hyperspectral analysis or something. And it's somewhat of an unexplored, not somewhat, it's almost an entirely unexplored area right now. Different energy plus resolution. Yeah, they might be. Yeah, there's 3 of them. I wonder if I just go scroll prize. I think we have it here. Yeah, so scroll 3 has, okay, 2 different resolutions at the same energy, and then a different resolution at a different energy. So you're right. Yeah, there isn't a one of like the same energy or a different energy but the same resolution. I think you're right. I don't think we do have any of that. That might be something that we have to think about. We're going to scan a ton of scrolls this year. I think we're targeting like 100. So we should be able to do something like that. We still haven't. I mean, a lot of this stuff like was testing out, you know, like they didn't know at the time what resolution do we need, what energy is the best, and so that's kind of an open question yet as well. It does. Okay. Oh yeah, right there. I'm staring right at it and I didn't see it. Oh, so we do have one. We do have, yeah, scroll 3 has 2 of the 3.24 resolution, but with 2 different energies. And so that's interesting. I mean, I don't think anyone's really done a whole lot with that. I think we have some of them registered with one of the resolutions, some of the surface segments, but not both. And so that might be a good test. And then the good part about scroll 3, well, it's not so small there, but it's the smallest one. So even though it's 4 terabytes for that, it's still small. But yeah, that's kind of I think that's kind of the challenge that a lot of people have had with doing any of this kind of analysis, and even really working with the higher res scans. We don't have a lot of native high res segmentations because it's 8 times the resolution, and so like segmenting takes so long, and the registrations are okay, but then you've still got this giant block of data. So I think a lot of people have kind of avoided experimenting with that one just because of that challenge. It's actually more than 8 times the data. It's a huge one. Yeah, so the file size is a huge challenge. I have 12 terabytes of SSD, and then I have a RAID array of hard drives, actual like spinning disk hard drives. But you can manage by using a lot of the smaller data. You know, most of the stuff that I do is on the 7.91 for exactly the reason you said. And yeah, there are also downscaled ZARs that are half the resolution. And those, in a lot of cases, for a lot of workloads, are a high enough resolution to do. Ink detection works with the time-as-former model on the half-res scrolls. So there's that. But it's just a challenge, to be honest with you. You've got to buy external hard drives or more hard drives. You can, with ZAR, if you use ZAR, you can stream ZAR over HTTP by just using FS-spec. That's very easy, so that's one thing that you can do. It's reasonably fast. I've ran a training using a ZAR volume on the data server, and it really isn't much slower, so that might be one method. We're working on trying to find good ways to present the data online. Our fiber team is using Webnosos, so they don't have to have any of the data locally. Also, you can segment in cards. What are ZARs? Yeah, a ZAR is a an on-disk stored NumPy array of data. It's different than like a normal PNG or anything. It chunks the data up into little chunks and stores it on disk that way. You can load them. The challenge there is that you need a couple different tools to load a ZAR. If you want to load them remotely, you need to kind of come up with your own method for doing that right now. You could use Cartez. I gotta come up with a good answer for that. But a ZAR is just an on-disk array of data, accessed a little bit differently than a normal picture, not a PNG or anything, and it needs kind of special tooling to open it. I can go through. This is something that that we need to answer a little bit better, I think, how to access the data easier. But it's something we're working on. You can also, like, if you just want to quickly see the data, you can go to, let's see if I can find it here. Nope. You get to see all of my. So one of the contestants, Jay Rudolph, has created this site if you just want to look at the data, and it's very handy for that. You can go in and look at the data from any of our scrolls. Say you want to look at scroll 5, one of the segmentations we've created. Let's just pull up this one. You can very quickly open this up and then get into the data without having to download anything. And he's got a couple different, you can tab through it. You can view the segmentations right on here, the segmentation and the ink predictions. So it's pretty nice to have that option. You can't do annotation in it though, and that's kind of one of the things that we're working on figuring out, is how to make it easier for people to get into annotation, because the downloading the data is a huge roadblock, and then not only downloading it but figuring out how to access it. So let's stop this one and run an inference quick. You can stop training at any time by default, and nnUNet saves every 50 epochs. If it does not improve the dice score, if it does improve the dice score, it saves a new checkpoint every single time it has a new one. And they get saved in nnUNet results, and then the dataset name, and then under your plan's name. So you can see in here, it copies these things so it can use them in inference. But you also get a progress.png, which gives you some kind of fancy graphs that are nice to see. There are some versions, there's some forks of nnUNet that write this to 1dB, but by default it just does this. And then your checkpoints here. So it hasn't saved a checkpoint. You'll have two checkpoints here if you let it run more than 50. You'll have a checkpoint best and a checkpoint latest. Latest is what saves every 50 epochs. If you want to do inference, though, if you stop it before it reaches 1,000, once it reaches 1,000, it would change the last one to checkpoint final. So if you want to run here, you've got to change one of these two to checkpoint final. Otherwise, when you go to run it, it'll throw an error. It'll say can't locate checkpoint final. So I'm just going to change this to checkpoint final, so it thinks it is the final. And let's run inference. So here you just do your input path. I'm going to change this. We'll run this on the fiber labeled datasets we just made. I have this in test datasets, images, and you can see I've got them appended with the 000 already, so I don't have to worry about that. And then I'll have it output to output test, sure. Then I put my dataset name, my configuration, my plans. I didn't run with those plans, so I'm just going to erase that. And then I'm going to add this line, save probabilities, which will save the softmax outputs as well. These are gigantic. Why can't I write to that? Do I have it already? Or did I not? Oh, no, I didn't. I tried to write it to a area I don't have write permissions to. There we go. So it'll print out how many it finds, and it'll start. The things are gigantic, though, if you save the softmaxes. They're uncompressed NumPy arrays, and they are huge. on here they don't look that big, but if you run a big block, these can be like 2.5 gigabytes each. And if you run a whole scroll, that's like 2.5 gigabytes for 5,000 cubes. So just keep that in mind if you save the probabilities. They store as NPZ files, and then you've got to convert them from NPZ to TIFF if you want, or you can read them right as NPZ arrays. But what I usually do is I save the softmax output, so with the save probabilities, and then I read every single NPZ and then rewrite it out as an 8-bit TIFF, and that saves a ton of room. You could also implement a custom post processor if you wanted to. That would do that for you, which I probably should do, but I've gotten by with the kind of messy setup that I do right now. I have a script written for that as well, which I think I have on my in my community folder, but I'll check. So I wrote ours to infer out test. Here you'll get slammed with these JSONs, which literally this is the spacing. All it says is this, just spacing 111. You can delete those when you're done with your inference if you want. I would keep these around though. It also puts your plans and some information about the inference. And I keep these around because if you do a lot of inference, later on you might go to say, hey, well, this inference looks really good. I wonder what my configuration was for that. Well, here you go. It's in plans.json. So let's see what these look like. I'm just going to open Nepari. And I'll do this too, so that we can see what the whole process looks like. But if we want to look at what the inference outputs look like, let's load this TIFF in Nepari, convert it to labels, and then let's load the actual image data, which I have under test datasets, images. This is scroll 1, 4097, 1497. Okay, perfect. So if we overlay it, we can see that this is how our model is performing right now, which is actually pretty good for only 40 epochs with, this is not the residual encoder or anything. That's our first one. I found actually sometimes models that you stop early can actually be better, even though the actual dice score might not be better. Just because as the model sees more, although it learns more complicated data, it sometimes becomes more overconfident that certain things aren't what you're looking for. Like, how do I word this? Or I guess it becomes more conservative, is what I should say. Whereas a less trained model sometimes is very overconfident, maybe in areas that it shouldn't be, but it can also be overconfident in areas that you did want marked in ways that later models might not be. I think I just copied the same one. I just want to look at a few of them. I want one of these 512s to finish. There we go. So that's 3994 S5. Kind of curious how this does. So pretty good. Again, you can see if you've got enough data, nnUNet can very quickly learn the data. We're only at 40 epochs over, what was that, like 20 minutes of training? And it's reasonably good already, probably as good as some of my earliest models, although my data set is much larger. But even after such a short amount of time, it's already learned what the recto surface is. It's not marking the back. In most cases, in some cases it makes a mistake, but not frequently. And if you look at it in the y-plane, it's actually reasonably good. Here it's made a mistake. Oh wait, no, it hasn't. That's correct. Here it marked a fiber, so it must be learning fibers. It's kind of fun to look at these. And then the softmax looks like this. Let's pull that up too, just so you know what that looks like. And you can load NPZs in Nepari as well. This has 2 channels. It has the probabilities for, nnUNet always outputs 2 channels, one for background and one for foreground. So this is the background probabilities. So it's 100% confident anywhere that's white is actually background, and then as you get higher up the grayscale, that is indicating its probability score for that spot. So here it's thinking, oh, maybe it's background, but it's not sure. And if we switch to the other channel, this is our foreground probabilities. And so you can kind of see if you look at these spots that the model isn't sure of. This one's pretty confident. It learns, like I said, it learns pretty quick. Like it's almost, what is that? Value is 192, so it's almost 100% certain that this is what it's looking for. Let's see, if we wanted to do a large volume, the way I do that is a little bit different. So if you wanted to say inference on a whole scroll, what you would do is download, you could just download the grids by default, the grids that are in the scroll volume package here. The issue with that, though, is when you go to recombine them, you'll have edge artifacts where you replace your blocks. And so what I do, and I have these available in my community uploads folder, and again, I need to move these so that they're available, or more obviously available. But what I do is I've created grid blocks that have 50 voxels of overlap in all directions, and then when I recombine them, I just trim that. And these are here, and so these are 600 by 600 by 600 blocks. Let's just see if I can load one of these. Every time I go to load one of these, I load one that is somehow no data. So I'll just throw one of these up in Pari quick so you can see what that looks like. Yeah, so this is just a 600 by 600 by 600 cube. They should be in nnUNet, but they might not be, so that's something to check. But yeah, that's all that is. That way when you recombine them with a script that I have, which I'll show, I think I might have it, I don't have it there. So I'm gonna put it in the Villa branch as well. It's kind of all this is kind of an in progress thing as I make a lot of the stuff that I've created over the last year or two more like generally available. I've shared a lot of these in different places, but I've never, well, because I was just a contestant before, although I wanted to share a lot of this stuff, it was difficult to find the time to place it in ways that were really easy to understand. This is a script that does the softmaxing I was telling you about. I'll make sure I put that one in the Villa repository. But what I do then to combine them is pretty simple. I just, it's called Zar from Grids. It should be, where did I put it? Oh no, it's grids 2 zar. So it just pre-allocates a array of the volume shape, and then it parses the names of the files, the XYZ locations, and then just recombines them to where they're supposed to go in the zar. But that's how I've done all of my models, is that way. It's just take the grids, run inference on the grids, recombine them. Looks like we finally finished that. Let's look at a couple more of these. I'm just kind of curious. I've never stopped the training that early, so I'm kind of curious to see how well it works. Let's actually do this too. Let's pull up a fiber label of that one and just kind of see. Change these to a different color. Sure. I like to look at them like this. I think it's easier to get an idea of how well they perform if you look at it from a Z or from an X or a Y, because you just get a better idea of like, is it really bad higher up or lower? The Z-axis I think sometimes is kind of deceiving, but these little dots are our horizontal fibers here, and this is an easy way to tell if you're in a different plane which side is the front or the back. As these are the verticals, and as they streak across the back, which is kind of hard to see, but those are our vertical fibers, and then the tiny little dots in this plane are our horizontal fibers. And so we've got a pretty good amount of overlap, but you can see as it kind of moves through, there's a number of areas that it misses. These are always the spots that are challenging, like right here, because they are mushy. But it learns those reasonably well as it gets along. Like we have, let's see when I ran. On a different one. So this is a more up-to-date model that I was training the other day, although it's not finished training yet. This is I was just kind of seeing how it was performing as it was going, but you can see this one is quite a bit better than that other one. It maintains connectivity all the way through, so it's relatively easy to use the tracer on it. This is probably the hardest part of these models, using them, and then using them in the tracer is that they have to maintain this connectivity. And it's so hard to train it to maintain that connectivity without creating areas that are merged like this, in the top left here, kind of. So it's a balance, because we'd almost rather have this than a huge gap there, because the tracer can kind of work through those as long as they don't stay that way forever. But it's a hard thing to balance, and that's probably like our number one issue right now, with our labels, is just regions like that. And then you can see also you get some of this weird, I'll put a mark over there. If you watch this right here, the one right above it, you'll see it for a brief moment connects to the wrong one, and then comes back and connects over there. And that is a little bit problematic when you go to run your tracing, because that's how you get a sheet switch. It'll follow the wrong one. If it's just short, it usually doesn't matter too much, but if they happen frequently and they happen for a long period, it's an issue. I think that's the end of the stuff that I had planned to talk about. I'm not sure. What else could I look at? We could start running inference on some of the newer ones that I was running. Why don't we do that? I'll probably end the recording here, just because the rest of it. No, I'll just cut the recording out for the nnUNet part. So I'll keep it going. Why don't we run inference on a couple new models and see how that's looking? I'm just going to drag a few terminal windows over here. I have this running on an AWS server right now. One of them, this one right here. But AWS has horribly slow disk speed, so the training runs really, really, really slow. I'm just uploading this to the data server so I can download it on my local computer. Let's do that now. It is expensive, yeah. We partnered with AWS and we got a fair bit of credits, so we use it. It's nice. AWS is nice in a lot of ways. But yeah, the disk speed can be a challenge. Although it's likely that I'm doing it wrong, to be honest with you. There's a very good chance that I'm doing something stupid and I'm causing my own issues. That tends to be the case. I'm just copying this entire results folder over to my local computer. Using arclone. You don't even need an H100, man. I ran like almost all my models up until November on 3090s, and then I ran the rest of them mostly on 4090s. An H100 for some reason also isn't really that much faster. I would just rent 4090s. It's cheap as hell. I don't. I also haven't seen a large increase in performance if I like crank the parameters up for the model. Like if I use a huge model, it doesn't really seem to work any better. Yeah, that could be interesting. Yeah, if you try to optimize huge batch sizes. So yeah, there's probably some stuff you could do there for sure. Let's pull up. So we'll run this medial surface recall, which is when Jordy made this recently. So let's change. I'm just deleting one of these older ones as I go through. Today at 540. Let's see the most recent one. And we'll run inference on the same thing, but with a different model. This will be 059. And this trainer is, if you ever need to figure out what your trainer is, by the way, you can just look through here because the file saves as that. And we want to save it to a different folder. We want to go to test datasets. And then inference. With 3. Yeah. No, we can do that. Yeah, so we can make a standardized R volume of that for sure. I got to dig up the script from Julian's done most of those, but we can absolutely do that. I'm going to write that down because I promise you if I don't write it down right now, I will forget. 6. All 3 energies standardized. Yeah, if you could do that, that'd be great. If you have other requests like that, always feel free to shoot them out. We're happy to put the data in formats and ways that make it easier for you to do experiments. A lot of this stuff is kind of just gathered up over time. We try different things out and uploaded them, and maybe some aren't in use anymore, or there might be better ways to store them. starting to get some back, so let's see how that goes. Okay, yeah, as you think of stuff, feel free. We'll probably have some more ideas for you too as we go. Like we're trying to add stuff to that like little asks thing as much as we can, just because, like I said, it helps have a starting point. A lot of people join the project and are kind of confused on what to do. That's not great. Well, it's a pretty tough volume, but I don't love that. Here's the other reason I do the merging of overlapping ones is as you get to the top or the bottom or the sides of your predictions, you get these like artifacts because it's half of the volume is, say the patch size ended here, but it was like this part, it's predicting on just blank space after a certain amount. And so the bottom and the tops of your predictions aren't very good typically. So that helps to give it an overlap to kind of eliminate those artifacts. Oh, that was from yesterday. I wonder. Okay. Yeah, that could be nice for sure. I was looking at a prediction from yesterday, not today, and I was wondering why it was so bad, but that's because it was from a very early checkpoint. So we've got 1497, 397. There we go. That looks more correct. So for a little bit, this one predicts something incorrect in the middle there, but for the most part, it's pretty good, likely good enough. What are we getting right now? What I really want to see is the 512 cubes. These take a little longer to run inference on, but to me, those are the more telling ones. It's just kind of hard to tell over 256 cube, like, is it good or not? Hey. 1084, 3994. Okay, let's see this one. Okay, yeah, so we're getting much better here. Let's look at this one versus that other one that we did earlier. I'm kind of curious. Just what the difference is on a 40 epoch one versus this. So yeah, you can see over the course of training, but it's still like, it's surprisingly good for 20 minutes of training. The first one, that's that brown one now. It doesn't miss a ton. I mean, overall, it's very important data. It doesn't miss a ton, but you know, these huge gaps are pretty problematic for tracing. But like, it's surprising to me how well that thing does. But this cube is absolutely good enough for a tracer, and probably not far off as good as we can expect given our current training data. There's a very difficult cube in here that I'm waiting for it to finish inference, because this is kind of my like oracle cube right now for our surface predictions, and I think it's that one, 9944994. But it's super mushy, and it has very low contrast. This is a pretty good scan here. Trying to find, yeah, this one. This is what we want to see. If this one is good, then we're in good shape. This one has a ton of noise and very low contrast, and it's mushy, and it has this, which is the most fun part, this kind of Z flip here, which you can see much more dramatically if you look at it from another plane. So if we can do well here, particularly in the upper left corner, this should be a pretty good model. Zero 994 04 994 is this what we're looking for. There. Yeah, okay, that's the one. No, it's not. I'm in the wrong one. There we go. That's the one. Okay, so we still got some work, but we're getting better. If we look at this in our other one, yeah, it's so close in a lot of these spots, but like you can see the difficulty it has in those spots because there's just not a lot of labels in those regions. At all, and I augment with lots of flips in that, but it's just data it hasn't really seen. Let's look at what that looks like in the very slim model. Yeah, so that's what that looks like in that model that we only trained for 50 epochs, which isn't great, obviously, but that's a challenge. Getting those spots. If this was segmented well, this corner here, if we could do that well, it's pretty much done, in my opinion, at least. That's the stuff that stops us right now. If we could get models that segmented this cube well, we're going to be in amazing shape. I'm going to run some other models on this one here in a second, and we'll see if this is one of them. But as soon as this one finishes, I'll try another one. We've got a couple models that we created here in the last few days. And right now I'm just trying to determine which one I want to run inference on an entire scroll for. It does really good just in the mush. Like that's as good as we can ask for in the mush, and that's as good as it needs to be in the mush. We don't need it to be really any better than that in here. It's as it rounds the corner there. That's the problem. Yeah, we do rotation. I rotate the cubes with 50% probability, but I don't know. For some reason, it just doesn't like. You wouldn't think, right? If you just look at this, You think that, okay, I mean, that's not really, from this plane, it isn't really any different than normal segmentations, and so it should be able to learn it, but for whatever reason, it struggles. Even with the rotations, like this looks like a normal Z slice of just kind of mush, which it's okay at, but even with test time augmentation and with rotations during training, I haven't been able to get it to go well. But you're right. I mean, just because I haven't been able to get it doesn't mean it can't get there. You know, there's a ton of things that people could try, and it's very likely that there's a much simpler answer to getting these to work than what I've tried. And maybe my augmentations just suck. I think we're done with that one now. Yep, okay, so let's try now. Mm-hmm. Yeah, so the rotation is applied like this in the training. So every time it grabs a patch, it has a 20% chance of being rotated. And it has a 20% chance of rotating along any of the allowed axes, which for my cubes, because they're all the same size in each dimension, means all of my cubes. So every patch that it grabs, it has a 20% chance. So I've essentially increased my total training size by, say, 20%. But it could apply more than 20%. But over enough, I'm doing it roughly 20% of the time. I probably should increase this, if I'm being honest with you. 20% isn't that much. Most of these augmentations aren't, the probabilities aren't crazy high. It can rotate over any axis. It's the allowed axes. For mine, it's all three. But if the shape was not equal in all dimensions, it would just be the ones that are equal. This one will pick a random axis each time it performs the rotation. But there is there would probably be some benefit in just rotating them ahead of time and then just removing that from there. One, we could look at it, which would be nice. And then two, we can guarantee that some set amount of them show up, or we could rotate specific ones, or that's probably something that we should do as well. Kind of curious how this one looks. This is using a trainer I haven't used yet, which is built into nnUNet. It's their like more heavy augmentation trainer. Let's see, can't find it, so what do I got wrong here? Plans, Resinc Unet plan, oh, Resinc Unet L plans. There we go. So I'm very curious to see how this one does. Yeah, that's actually, that's a good idea too, right? I guess right now I'm only rotating over X, Y, or Z, but it doesn't even matter. I could rotate over, yeah, anything. And I also think that like we could use I added a transform to this one that I just called a smear transform, but what that does is take like the 3 slices before it and overlays them with a little bit of like transparency or opacity, so that it kind of blurs it with the data from around it, which I think works reasonably well. But coming up with some augmentations would be sweet. I mean, if you can come up with ways, I should add that. That's a great idea. If you can come up with ways to augment data, take a cube that we have already that exists, that labels exist for, and modify it and the labels such that it looks like mush or strong bends like this, that would be huge. As long as the label and the image stay, in the same place or overlaid properly. And you could do it. You don't even have to integrate it into a trainer. I can put pre-processed data in there. It doesn't have to be integrated into the trainer. And if you came up with that, I mean, I could integrate it into the trainer too. I should put that on the list. I didn't even think about that. Been trying to fix that issue with my own thinking for a while, and not even realizing that I should just put it out there that I have trouble with it, and I can get some help with it. That makes a hell of a lot more sense, doesn't it? Surprising. Decent. Yeah, like you said, I mean that's a thing, right? You just got to think about it. There's a lot of things that I've done that, like, after I do them, I'm like, okay, that was so obvious. I don't know what took me so long to think of that. And I've done a fair bit of volumetric data analysis. I've looked through using Dragonfly. I've looked at the data a ton in 3D. I mean, I labeled a huge amount of letters fully in 3D, so I should have thought about that, but I'm glad you brought it up. I had thought about doing some pre-computed augmentations before, but yeah, it's I'll send a link right here. 1 second. This is the root of the nnUNet one that we're using right now. But again, if you and then augmentations actually exist within. Let me send you one more thing. I use this as the batch generators for me. I have I hate to call it a branch because it's not really a branch. I have the whole thing just copied and saved into there. And if you want to look at how a batch generator's transform is written, there is this, which is the basic transform. But essentially, all it does is nnUNet data, as it moves through the pipeline, exists in a dictionary, and then there's just image, seg, and then like prediction, and you can just see those throughout there. But that's the only thing different about it, is you've got to access it as a dictionary, and then you just use the class method, apply to image or apply to segmentation or whatever. It's not too hard to make. But you can just subclass basic transform and let it handle a lot of stuff for you. What I do too, typically when I add stuff, although I'm not always the best at it, is just put a main block at the bottom so that you could run it with a, you could run it like with a sample locally and actually see what that looks like. Hopefully we have, alright, we've got a 512 here shortly. I'm gonna run and fill up my water real quick. I'll be right back while that runs. Okay. So maybe now, the only issue with running a 14900 and 23090s at your house is that your office is about 5,000 degrees at all times. I wonder, I might have made this model big enough that it's spilling onto the CPU because it is running slow. Oh, that's my AWS instance. It's hot though. Open a window. Yeah, data center server. That would be sick. I like to do a lot of stuff locally though, even when I have like cloud credits, because it's just easier to very quickly visualize stuff. I've used a lot of cloud offerings, and I've got credits right now. I can run stuff online without using any of my own data, or my own money. But like, for most instances, not for most, but for a lot of instances, there's really no benefit for it for me because I have to do all the setup of getting the data, and then I've got to get it in the right place, access it, install all the dependencies for whatever I'm running, and the process of that is kind of a pain sometimes. But when you're doing inference on a huge volume, then that's when those benefits of having, 8 A100s make it make sense. I have a 14900K and two 3090s, and then I have 128 gigs of RAM, and then my disks are, I have an 8 terabyte NVMe in a RAID 0, so just striped with no backup at all, and then I have the same thing in hard disks, but 64 terabytes of it striped over 5 14 terabyte disks. but you don't need anywhere near that. If you got a 3090, I mean 3090s right now, maybe not quite yet, but they should come down quite a bit in price. But with just a 3090 and like 64 gigs of RAM, you could do 95% of what you'd ever want to do, at least with this kind of segmentation. It's not like large language models where you need like a billion gigs of VRAM. You could sneak by probably with even like a 4060. Yeah, 12 gig 3060 or a 40. I think the 4060 Ti has 16 gigabytes of VRAM, and you could pick that up for like $300. I'm pretty sure. Anything with like 12 gigabytes to 16 gigabytes, you could sneak by with. Or you can run cloud instances are so cheap right now. You can literally rent a 3090 for like 30 cents an hour, and you don't need that long. I actually do. I do a fair bit of testing on cloud instances on like 30 or 40 90s, and a lot of them you don't really need to do anything crazy. Like I can't really show it right now, but you can just open up on a significant number of them. They have Jupyter notebooks that you can open online, and so you're kind of interacting without having to use SSH or anything if you're unfamiliar with that. I use the Jupyter Lab terminal a lot just because, not terminal, but I don't know what you'd call it, window or connection or whatever, just because sometimes it's nice to see, I think sometimes it's nice to be able to like actually like visualize the data you're working with and see the folder layout and stuff, but a lot of people have preferences for different things. Also, if you run it on, like, the issue with SSH, if you connect with SSH, is if your computer shuts off, the terminal closes, and you kind of lose half the benefit of actually running it on a cloud server in the first place, unless you use a web terminal. Or that, yeah. Again, see, issues that I've created for myself that I have to find solutions for. All right, let's see if we got some large ones now. By the way, if you need help getting set up on anything, hit me up. I'm happy to help you get set up on a cloud server. I mean, we can't pay for it, but I can give you like technical assistance with figuring out how to get your data over there, get it transferred, or anything like that. Waiting for this TIFF to show up. There we go. This one's pretty good, actually. Got breaks, which suck, but doesn't make any mistakes, it doesn't seem. I wonder, so a lot of times what I'll do is take multiple models and ensemble them, and sometimes models that aren't great on connectivity do a good job in other areas, and I'm going to see if this one gets anywhere that the medial one I was showing earlier doesn't, and if it does, I might keep it around and ensemble them. That's wrong. So this one it marked back here, but that's actually a Colesis, so that's not correct. So this one doesn't seem to really, maybe a little bit right there. We get a connection, which is actually important. So maybe I keep this one around, but I might have another model that just does that spot better. But this happens frequently, where I've got, you're on an M2, yeah. Yeah, you could for sure. You could do inference on M2s reasonably, but training is going to be really, really, really slow. I think what I would recommend honestly is finding a cloud server and doing your annotation work and all your programming and stuff to get all your models set up locally, and then renting a cloud server. Because if you rent a 3090 at like 50 cents an hour, I mean, I don't know what Vast AI is at right now, or TensorDoc or RunPod or Vast, but let's like there's so many of them, but like, yeah, 25 cents an hour. So you could run your training for, an entire 24 hours for like nothing, and it's not like you're going to be training all the time. You're going to be training, and then say you run a training for 24 hours or something, which most models won't take that long even to train. Then you're going to, make some changes, maybe get some new data, and then kind of plan your next training run. But you're not usually going to be training all the time, so it's reasonably cheap. I did most of my training before I got my better computer setup now, just on cloud instances with an M1. Yeah, you can set limits too, though. Like you can set like be careful with this because it'll just kill your instance if you aren't paying attention. But you can set limits on the amount of money that you want to spend at a time. Like you can load your instance up and then set like a maximum spend or a minimum balance that you want to go to, and it'll just kill your instance. A lot of the horror stories that you hear about cloud prices are typically actually from AWS, where people don't realize that S3 has like reasonably high ingress and egress costs, and they won't realize that as they're transferring terabytes of data or have made like an API open, that people can just hit that and just smoke their AWS S3 bill. The compute's kind of safe if you are smart about it. We got one more coming up. Yep. What do we have? I'm just looking through here, seeing which one I want to grab, which is 3994, which I think is our most recent bad one. Very strange. No, the model can, I mean, the model could hallucinate, I guess, but it's not as much of an issue with computer vision in the sizes that we're doing it in, right? Hallucination is usually immediately obvious in a segmentation model. It's pretty clear if it's hallucinating. Like, if you look at the data and there's a line, straight across here, then I know that it's making something up. But it's not as big of a issue with segmentation models as it is with large language models, because you have a immediately verifiable image right behind it. It does happen in that you can force models to do things that maybe you don't want them to, but yeah, that's essentially what we're trying to do. We're trying to make the model robust to rotation, and so it doesn't associate a specific rotation or a specific orientation of the data to a segmentation. I'm surprised that TIFF's not in here yet. But it can be an issue though, if you overtrain the hell out of your model, but it's kind of hard to do on this data, to be honest with you. And even hallucinations as they can occur on here aren't usually so much a hallucination as you would understand in LLMs, in that it's making something up entirely. What it will do if you've got a badly trained model is maybe it would connect these two where they shouldn't be, or it'll extend this line out thinking that the line is supposed to continue, but maybe it isn't. They're not really like, they're not as crazy, you know, as you see with LLMs. But that's part of the challenge, though, is again that we would know all those things a lot more if we had better metrics, and we're trying to come up with those still. But it's an ongoing challenge. In this challenge is coming up with proper metrics for these kinds of things where there is no ground truth data. You know, I mean, there's ground truth data in that we create it, but it isn't like, especially with ink, it's not like provable, you know. I mean, it's provable in a way, but you can't look at the sheet, you know. You can't pull it out and unroll the scroll and look at it. So you've got to create the ground truth data by kind of just iterating and then verifying that matches up with the scroll data. It's not as easy to create ground truth data for this. Although I just looked at this one. 4994. Yeah, it does. And the good thing is that we've got, you know, the methods that we use account for that in a way, you know, at least the tracer does, in that it takes a consensus of a number of them. So when we run the tracer, we create a bunch of patches, and from these patches, say this sheet right here would have 20 overlapping patches, and maybe two of them, there's a line here, two of them go over here and we're on the wrong one. Ideally, a number of them, the number of them that continues along the correct path is greater than the number of them that continues along the wrong path, and then your consensus would say, the consensus agreement in the solver would say, you know, let's take the more agreed upon path. But that doesn't always happen. In certain areas, you know, maybe the misconnection is so strong that more often than not you go the wrong way. And then you've just got to go in and address that later. It doesn't happen that often, though, at least not as often as you would think. But it does, and that is, yeah, it is very important that we have accurate models. It's difficult to make. It's just difficult to generate. All of these labels were created manually with a program called Volume Cartographer, and it's hard to create super accurate labels with that, and manually labeling one of these cubes would take you, I don't know, days, multiple days, to make one of them probably, because you'd have to annotate every single slice manually. So that's a challenge. That's I've got a call for that out on the prize section. If people can come up with better ways to make labels, we're gonna throw money at them. We need them horribly. So if you've got any ideas along that path, I can help you get started there. I can show you how I create the labels right now, and if you've got any ideas to improve that, I'm all ears, man. It's another instance where you can see like this other one in certain spots is a little bit better. So I think I'm going to end up with another ensemble that we have to do. I've been hoping that I could create a single model that is better than ensembling 4 of them together, and I haven't been able to do that yet. And the reason I don't want to have to is I have to run inference on a whole scroll for, say 4 models. It takes forever. But I haven't been able to get one model that does as good as 4 of them smashed together. But this combination looks reasonable, actually. If we consider what's behind it, which is a relatively low contrast pile of mush. I mean, that just looks like noise. So you can see the difficulty of segmenting some of this, because that doesn't look much different than if I were to just create random noise. Let's see. I wonder how big that I was looking at. I'm going to create a little bounding box quick, equal to my patch size. I'm kind of curious. It doesn't tell me on there. I wish in Nepari it would tell me. I guess I could start from a corner. Let's just do that. That would make the most sense. Considering it's a square, I should be able to just start from a corner and go up 190 pixels. And then negative 190. Which should take me to... What is 512 minus 190? Now we get to watch the stream of Sean tries to do math in his head. It'd be, what, 320 something? Let's just say it's 320 for fun. Because maybe it is. It isn't, but it's close enough that it doesn't matter. So this would be the view that our model has. I need to make the edge color, or the face color, transparent. Yeah, so you can see why that's so difficult for the model, because all it's looking at is essentially noise. And that is an entire patch size. So I have to crank my patch size up, but the challenge with that is that I don't have very large sections in most places that are densely labeled for that size. Bet you. Yep. In that spot. I wonder if I do the same. How do I get to that layer again where that was? Where is my square? Now let's just do it again. I should have enough context there, but I guess that's my next one. I'm gonna take my patch size. Why don't I start one of those right now after this? And I'll do this by just going in my plans here. Well, I'm actually gonna have to make new. I'm gonna have to make new labels, or just take only the labels that have a large enough size, which we'll find out if we even have. How many do we have that are greater than 256? Maybe 800. Yeah, right. What Forrest said is essentially correct. What these models are doing is when it looks at an image, it's trying to create essentially a really fancy filter, and it looks at an image and finds which patterns correlate the most with the labels you've generated. So it applies a bunch of filters, say, to this spot right here, millions and millions and millions of times. It applies different filters to a spot here, and when one generates an image that matches your label data, it saves that, more or less, that filter. And then it runs a bunch of filters again, and it checks, and then when it finds one of these things, it's called a feature. And then it runs a bunch again, and then it says, okay, well, we've got a little more of this. All right, we'll continue along that path. And it essentially just applies filters to an image millions and millions and millions and millions of times until it gets a set of filters that produce the image you're looking for. It doesn't think in that way. It doesn't really know. It doesn't know what it's doing. So we're gonna find. I'm gonna see if I've got enough labels that are large. It's 236. If I've got enough labels that are large to train a model on, I have a lot of 192 or 172 labels, which really limit my patch size. But I think anything that's 9 megs is 236, so I could crank my patch size up by 50. Yeah, let's try that. This is going to be a bit of a challenge in that I've got to find out. I've got to delete the same images and the same labels. And I could probably just script this, but I don't feel like it. Oh, that's not ideal. These don't have a clean break. All right, 1 second. I forgot I compressed the labels. We could script this up manually, or I can just have ChatGPT provide it for me, which seems a ginormous waste of ChatGPT's abilities, but for me right now, that's what we're going to do. And then I have a Python notebook that I just kind of keep around to test things out in. No, I don't want to do that. So all I've asked ChatGPT to do is give me a script that looks at the images in this folder and looks at the images in this folder and any that don't exist in this folder to delete them. And I didn't actually check if this script is written properly, so I might just end up deleting all of them, but it looks good to me at a glance. So let's see what it does. Okay, it didn't delete all of them, so I think we're good. Cool. Okay, now we need to modify our dataset.json. Our updated train number of 875. And then we will pre-process that. And we have to change the dataset name because we can't have multiple datasets with the same name. Remember what the planner is called. You'll see I end up going to this repository all the time. There we go, that's what it is. It's -pl resinc. And we'll do M. That should be good. Oh yeah, I want to set my number of processors to 16. Is it NP? Oh, it's just NP, not NP. This will take a little while longer than our other one because I have 10 times the training images in it, but it shouldn't be too bad. And Polytrop, what we've done at this point is just, I went through a slide and kind of talked about nnUNet for a while, and now I'm just I'm looking at some segmentations produced from some models that I trained over the last few days, and then now looking at the data overlaid over the scroll, I'm realizing that in many places, my patch size probably isn't big enough. So the reason I think this is if I zoom in on, certain areas like this, this is about my patch size, so this is about what my model sees. Actually even a little smaller than that, more like this. The model's really only, it's just noise. It doesn't have enough context to determine really what any of this is. If it's looking at this right here, how does it know where a fiber is? It's just noise. And so what I'm going to do is increase my patch size, in the hopes that if it gets more this much context, it's a little easier for it to decide. I do have to reduce, in doing that, I have to reduce the Z dimension probably, but I think we'll be okay. Wait for this to finish. I got one more scroll 5 prediction out. So it's not Python main.py. So when you install nnUNet from there, I need to add this to the slide. CD into the nnUNet repository, as part of that. So it's under segmentation models. Let me just pull it up quick. Make sure you have Torch installed first. Yeah, no, they're not. You don't ever run nnUNet from the script. You never call the scripts. So if you've got it started, you would just do nnUNet train or nnUNet. The commands are all in here, but you would call nnUNet train, nnUNet preprocess, whatever. It sets them on your path, so it just finds them that way. It is weird. I'm going to just copy this, but when you do training, oh, you do, okay. You could maybe, the entry point, so all that's calling, the entry point is actually this. It's under run. There are entry points, so you can do that. I think they're under run, yeah, run training. So that's the training entry point, and then the entry point for inference is under predict from raw data, I think. I'm going to see here if test data sets. No, it's just test data sets right here. That most recent one should be done by now. 5494. So that went reasonably well too, but this is a pretty easy one. Okay, let's see if this is done pre-processing. Yeah, that's okay. So we should have here now, now that we've run our pre-processing step, we should have in our pre-processed our plans, which we do. Although, well, why did it do that now? Plain conv unet is not what we want. All right, well, I'm just going to copy a plans file from a different one. I can't do that. Why? Not found in plans file. Well, I know that. It found the planner, but it didn't find... Huh. I wonder if I can just run plan experiment. So you get to see me troubleshoot an error I've never seen before. Yeah, so it already threw that error, which is wrong. Oh, that's why. I missed the dash. It's all adding up now. I'm surprised it even got that far but without throwing an error. Okay, so we're just going to go down to our 3D and we are going to modify this. I want my patch size to be 200. What was my smallest one? I'm just going to set my patch size equal to my smallest image, which I believe is 236. And then my next size up would be 512 images, or 320 images actually. I have some 320s in here, I think. No, maybe not. $300, so I'm just going to think about that a little bit, but I think that'll be fine. Because it'll just mirror. Yeah, that'll be okay. So we're going to set our minimum patch size to 236. If we do that, this is ZYX, so I need this to be 236. Well, it can't be 236, it has to be 224 or 256. Let's do 256. Trying to think of the right size I can fit here. We'll try 96. I don't know if I'm going to be able to fit this in my graphics card. 256 is very, very, very large. And I'm going to try to change this too. I want to add another stage. It gave me kind of a conservative network because I used the residual encoder medium planner, which tries to fit it within like 11 gigs of RAM or VRAM, but I have more than that, so I'm just going to manually modify the files. I think I got it right now. All right, let's find out. I think that was the name of them. I'm just double checking that my plan's name is correct. I'm just going to copy it. Oh, I got to change my dataset name to what the actual dataset is. Modify my splits because I don't want to waste good training data. So I'm just going to rip most of the S4 ones out and most of the S1 ones out and only keep like 50 or so around for validation. Maybe even less. Let's see how many that is. Yep, I'm missing. And put a comma there. It shouldn't. Everything else looks right? Yeah. There you go, 33. That's fine. Now we see if we can fit this in my graphics card. It's good practice too to just check in here that when you make any changes that they've actually reflected in here. That's not always the case. Maybe you did something wrong. They should show up in there, but sometimes you do it wrong. But I've got my additional 320. I've got all my additional kernel size configurations, and then somewhere, there we go, end stage is 7. So we're good there. What it's doing right now is breaking. But why? Oh, right. It has to be a multiple of... Yeah, I've got that wrong. I have to be able to divide one of them by a certain number. And I can't remember what that number is. Somewhere in here it'll tell me. Right, there it is. Number of times a pool, so we need to know how to pad the image size. The pool input images must be divisible by 2 times 7. Right? Here. It's not 7. Let's see. Nope. Maybe it doesn't like my patch size being larger than my image size, so let's just try 224. This is the fun part. Yeah, okay, that should work. No. Come on. I know it. You don't ever run into this if you don't modify the patch size. 2, 320, 244. Did I add? Maybe I added 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. That's correct. 1, 2, 3, 4, 5, 6, 7. 1, 2, 5, 6, 7. That's all right. That all should be good. might be introducing too many pooling stages here, and my brain isn't functioning at full capacity at the moment to double check. All right. Oh, right. There we go. I was introducing too many pooling stages, and I was running out of image. The way you could change that is if you reduce your, there is a parameter in here. Where's numpool per axis? Maybe it's not in the plans file, but you can change it where you would just make it so you don't pool the same amount, or you don't pool at all in a stage. But we're just gonna leave it because I don't really think it's gonna make a big difference to add another stage there. I was just kind of doing it to show modifying plans files, but I still did change the patch size pretty substantially. It started out at 128 in all dimensions, and we've gone to 256 or 224 rather. In X and Y. Which is an increase of 40 pixels in all dimensions from what we were running before. A little less than 40. No, I haven't. Could be interesting. I've used 5 by 5 by 5 before, not in an nnU-Net, but theoretically it could make a bigger difference. Or if I increase the stride or the dilation, which you can do in there as well, so that would give the kernel more visibility, theoretically. I've kind of stuck with the defaults here just because, I don't know, actually. I just have. But there definitely could be some stuff that could be changed there. No, it helps in the same way here too. Basically it's the amount that the kernel can see, So it absolutely could make a difference. It's just something I haven't tried. Probably something I should. That's the thing, is just so much, yeah, it does, and there's just so much to try. There's so many different parameters, and each training run takes quite a long time. So trying them all out, especially when I was towards the end of the competition, it was like kind of a risk in a way to try something out that I didn't really know if it would have an effect. So there's so much room for improvement on these surface models, dude. Like so much room for improvement on them, and not even through like crazy changes, just like simple changes, testing them out and then verifying their if they made a difference or not, and then documenting all that in one place. That's something that we've got to do a much better job of. It's just hard, which is why I'm trying to get the data sets out there and available to people so that. And then running this little nnU-Net thing and recording it, I want to get people running machine learning models as much as they can. A lot of people just think that it's extremely complicated, and it's not really when you break it down. If you take the defaults in nnU-Net and just make little changes like that, change the kernel sizes, anybody can change a 3 to a 5 and run that, see how that goes. That's not super complex. But you're right, data is the winner all the time, and data is the only thing that, not the only thing, but by far the most important thing. A crappy architecture with kick-ass input data is going to beat, the most complicated, insane architecture ever, every time. So I'm curious to see how this one runs with a bigger one. The most I've been able to get out of this recent data set is like 61 to 62% on my pseudo dice. So I'm hoping I can get something a little bit bigger. This is my first test of actually expanding that. Although I lost 900 training images, which sucks, but it might not. A lot of them are the same basically anyways, so it might not really matter. But I'll run this one for a while, see how it goes. Probably run it. I usually run them for it runs for 1,000 epochs, so depending on the epoch time, I'll run it for 1,000. Although I need to cancel this because I don't think I used. No, I didn't. I need to stop this one and use. Use a different trainer. Actually, you know what? Why don't we take this opportunity to increase our rotation and some other things. So let's increase our percentage of rotation to like 0.5. Set our magnitudes. What is our? We'll change that to true. Do elastic deform. I can't remember if it's a magnitude or I gotta go into the trainer quick and check. I have it set in a different one. So we've got it to 50, which seems reasonable. We'll increase the magnitude of our deformations a little bit. Increase the chances of all the rest of our augmentations. That's going to slow down my training a little bit because I did, didn't I? I changed that one and then I didn't revert that. It's going to increase my training a little bit because the elastic deformation is a pretty expensive transform, but if it works, you know, I'll take the slower training time for a model that's more robust. There's kind of a balance to be found there in that it limits the amount of training runs you can do as well, but I think it's worth it. It should help simulate some of the more mushy or more curved areas. But you can run this too. I've never tried it yet, really, actually. nnUNet theoretically should work on ink too, if a person wanted to try it out there, and I think it should work just fine. The only thing about it is that nnUNet's patch size is going to be well above the suggested 64, but we don't have a competition right now. Well, we do have a competition, but we don't have currently any, like, I don't believe that we have any hard set requirements on patch size. So you could increase it. There's just going to be more scrutiny there if you've got a really large patch size. Now that doesn't mean that it would get declined necessarily, just that we would want to verify that it isn't hallucinating in some way. Probably by just running it on a scroll with known ink and comparing that. But it could help. A larger patch size certainly could help with ink detection. I'm just going to see how this one goes. Got about 8 minutes left. I'll be here, and then I'll have to go get something to eat. I have not eaten yet today. I've just been caffeine all day, more or less. Second, I'll be right back. All right, sorry about that. The cat was banging on my door. Okay, so there's a nice start, 33. That's a huge start, actually. The first epoch is usually a lot slower, just because it has to unpack all of the data first. So 212 isn't terrible. I mean, I'd like to see it a little bit lower, but it is what it is. I'm kind of curious how much of my GPU I'm using right now, because I could potentially increase one of the spatial dimensions, but I don't want to fill my GPU completely up, because then I increase the chances of it crashing, considering I'm using the one that I have. Yeah, 20 gigs, that's not bad. I can run with that. I'm gonna have to try to generate some labels that are huge, actually, now that I think about it. Yeah, I've done that in the past, and I actually keep forgetting about it. That's a great idea. Thank you for reminding me. Yeah, I haven't seen. I've limited, so my 3090s are what, 350 by default at the max, and I've limited mine as low as like 280, and seen almost nothing of a drop in performance, and they run so much cooler. I mean, at the end of the day, if you're talking about an epoch time of 212 seconds, and it drops down to like 200, does it really matter? And it kind of keeps my room colder and everything else colder. Well, I don't think they're running too hot right now. 83, not ideal, but I've seen worse. They can run pretty hot. 86 is pretty damn hot, though. Let's see what it's at now. '86, yeah. 86 is a little warm. A little warmer than I'd like. So, yeah, I'll probably have to... Yeah, I'll probably just do that right now. Let's just try 290 for now. See how that goes. All right, let me out of here then. NVIDIA SMI doesn't want to give it up. Come on. There you go. Try that again, see what happens. Yeah, I mean, it's not that different for this either. Like, my batch size isn't that high. Really what takes the most time is loading the data, and most of the stuff on there is just the fact that my images are larger than my batch size most of the time. So it's not even using all of it at once. So what do we have? 212 for the first one, I think. Let's see what we get on this one. Epoch 0, 212. It's crazy how much heat these things generate, though, dude. Like, I just replaced my cooler with a like 420 millimeter 3-fan AIO that's set to intake, so it's intaking, cool air, and I still can't keep this 14900K cool. And I could underclock it, and it's fine because it can run at insane temperatures. I mean, it's meant to run at crazy temperatures. But it's just a pain. It's insane how much heat you spit out with the 3090 and a 14900K. It's just unbelievable to me. It's not nice on the power bill either. We'll see how this one runs, and then I'm going to take off. And then I got to find out how to cut this video up a little bit. Although I could just keep the full 3 hours. Depends what people want to watch. Hey, Hannes. You came in right at the end, unfortunately, but you got a little bit. I'll be here for a little bit, maybe another minute or two. Just waiting to see how this first epoch of this training run goes. Trying to figure out a way to get my graphics cards not to melt. Come on. Let's see if it's cooler now. Okay, 219. That's not bad. So 7 seconds longer of a training time, and we dropped 7 degrees Celsius. I think we can handle that. But yeah, all right. I'm taking off, guys. I gotta go eat, take care of a few things. So I'll be back tomorrow. I'll have the video uploaded not too long from now. Have a good rest of your day. Bye.